This is the 1990 mechanics question 1. Right, and this is a problem that requires a little calculus to get the what they want, right? So first question, you've got a block sliding towards the right with an initial velocity v naught, and so it's got a mass m, and there's a resistive force acting on it towards the left, and that force is minus kV, so that force depends on the velocity of the block, so it's not a constant force, right? And the first question is they want the acceleration. They want you to derive an equation for velocity as a function of time and sketch some graphs. And so this is a really typical type problem that shows up a lot. So you should know how to work this and variations of it. Right, so here we go. Free body diagram. So first of all, let's see, here we go. So there's the weight of this guy, mg. There's a normal force acting up, and there's this resistive force, minus kV. So there's your free body diagram. And then the initial acceleration, magnitude, and direction. All right, so that would require writing down Newton's second law. So net force is ma. Then we switch over to calculus land. So that net force is minus kV. And in calculus land, A is dv dt. There you go. So you'll get points just for writing down this differential equation. Okay. And then they want to know the initial acceleration, which is just dv dt, so then divide both sides by m. All right, so the initial acceleration is minus kv over m. In other words, it's to the left and has a magnitude of k v naught. Yikes, that v naught. Because that velocity is going to start changing, right? But the initial velocity is v naught, so there you go. That's the initial acceleration. And then they want you to derive an equation for velocity as a function of time and sketch it right here. All right. So let's do that. On the next page here, velocity is a function of time. So I'm just going to make a little sketch here of this setup. So it starts off at 0, 0. So find v as a function of t. Okay. So let me write that Newton's second law again. Again, starting from scratch, net force is ma. The net force is just minus kV. And a is dv dt. So if I want velocity as a function of time, it's all about getting together the v's all on one side of the equation and whatever's left over with t on the other side. Right. Because this little v right here, that guy really wants to be with this little guy over here with dv, right? So we could just cross multiply, and then that's going to turn into minus k dt over m. Okay, so again, what did we do here? Well, I divided both sides by m, and that's going to get rid of the m. Then multiply both sides by dt. And that makes that guy go away. And what I'm left with is minus k dt over m equals dv over, yeah, divide both sides by v also. I know I'm making a mess here. Yeah, so v over v on the left cancels out as well. So I end up with dv over v on the right. And there you go. Now you integrate both sides. So on the left, I'm going to integrate from 0 to t, and on the right, I'm going to integrate from v naught to v. Okay, let's make a little more room here. So on the left, let's see, the integral of k dt over m is minus kt over m. And on the right, the integral of dv over v is ln of v from v naught to v. It's a definite integral, right? Both sides here, okay? So then, proceeding, let's go to the next page here. Right, so I had minus kt over m. Okay, so then if I, on the right side here, ln of v from v to v naught, so that's going to be ln of v minus ln of v naught. And then you will recall that ln of v minus ln of v naught can be written as ln of v naught over v. No, ln of v over v naught. Right, okay. Yeah, and that is an ln here. And then finally, then here to get rid of this little ln guy right here, exponentiate both sides, which means we do this. And that e undoes the ln. And so then that's going to give us on the left e to the minus kt over m equals v over v naught. And now just multiply both sides by v naught. And there you go. Let me flip it around though. So that's going to give us v is equal to v naught times e to the minus kt over m. Voila, done. Okay, let's look at this for a little bit. You should practice this type of problem pretty much every day until you can do this quickly and efficiently and without too much stress and strain, right? So let's just check this out and see again. Let's look at what this thing is doing for t. So for example, let's say at t equals 0. What is v going to be? It better be v naught, because in the problem, that's the initial velocity. So yeah, if I put a 0 here, times 0, well, that means it's e to the minus 0, which is 1. And v naught times 1 is v naught, so that works out nicely. Okay. And then what about after a long time. Yeah, what's a long time? It depends on the problem. Okay, it could be microseconds or it could be years. Okay, so let's write down that equation again here. Okay, a long time, that means that t approaches infinity, okay? So that t right there, that gets big, okay? So e to the minus a very big number becomes smaller and smaller and smaller and smaller and smaller until it reaches 0. So after a long time, the thing on the right here turns into 0. Bloop. That means it stops, which makes sense. After a long time or moments, this block is going to stop. Okay. Then, if I look at, you should be able to then, based on this is a pretty standard exponential decay type problem. So then, okay, so again, let me redraw the initial object here. So we'll go ahead and do all 3 graphs here. And this is the positive direction, is towards the right. So position versus time. Well, it's moving in the positive direction as a function of time, but then it moves slower and slower and slower and slower until it finally stops. So that graph is going to, there's an asymptote right here, which they may ask you to find. And that guy looks like this. Right. And then v as a function of time, it starts off with a velocity v naught, and then that decreases nice and smoothly until it stops with a v of 0. Right here, okay. And then acceleration as a function of time. It starts off with a negative acceleration, right? In fact, so that initial acceleration is minus k v over m. So yeah, down here. And then that acceleration gradually approaches 0. So that's like that. And there you go. Okay. And again, if this problem shows up, scan through previously released exams. Also, this is very commonly, there will be multiple choice questions about this type of situation. So there you go. Done.